everybody, and welcome to our next video. So for today, we are going to be looking at implicit differentiation. So up to this point, most of the functions you guys have worked with in past courses have always been written in explicit form. Really, the only exception to that is when you work with standard form linear equations. So something that looks like this guy, 2x plus 3y equals 4. So this would actually be an implicit equation. So the difference between implicit and explicit form is explicit form means that one of your variables is defined as being dependent on the other, which is a fancy way of saying one of your variables was isolated. And when we do this in most circumstances, we solve for y. We always treat x as our input or independent variable and y as our output or dependent variable. So because of that relationship, we like to write y as a function of x. So this is a quadratic function written in explicit form, y equals 3x squared minus 5. Again, when it's in this format, if I want to know the output value, I have to first input something in for x, do the math. And because we isolated y, all of the math is contained on that x side. So that's why we say that the value of y is dependent upon the value of x. So when a function can be defined explicitly, we could take the derivative using all of our normal rules, and that's a very straightforward process. We have all of the different rules that we've learned up to this point to pick from. However, there are some functions or some relations that can't be written explicitly. So sometimes we have to work in an implicit form like this. When it's written like this standard form, a linear equation, you can't tell which variable depends on the other because they're kind of mixed together. We haven't isolated one variable, so we haven't really identified that input-output relationship. So when they act towards each other, like at the same time, finding the derivatives a much more complicated process. So let's take a look at an example here. So there are some implicit form relations that we can isolate the variable for, like this linear equation. I can get y by itself and puts it into mx plus b form, and then we can take the derivative from there. This guy is actually a rational function in implicit form, xy equals 1. So if it's possible to isolate a variable, again, we typically choose to isolate y, but it technically doesn't matter. You could pick either. But when we isolate y, we would divide both sides by x, so we get 1 over x, or x to the negative first. This would be a power rule, so to take the derivative of y. Uh, Another idea behind this explicit form and the idea of inputs and outputs, because we define it as y being dependent on the value of x, that's why we come up with this dy dx notation. This signifies that x is our input, and we want to know how does the output value change as we change the value of x. If we decided to solve for x and make it x equals 1 over y, when I go to take the derivative, now I've said that x depends on the value of y, so we would actually flip it around and do dx dy. That's not something that we normally dive into. It gets a little hairy and complicated, but just know that the naming of variables is kind of arbitrary. It's just something that we've accepted along the way, that x is our input, y's are our outputs, but we're not beholden to that. So if we could put it in an explicit form, though, taking the derivative, this is just a straight up power rule, and we get an explicit form for the derivative. Dy dx equals something that depends on x. However, it's not always going to be that way. So consider this equation. X squared minus 2y cubed plus 4y equals 2. Right now, this equation is written in implicit form, and it's impossible for us to write this as a function of x. It's impossible for us to get this into the form y equals some function, some expression that's using all the different math operations with just the x variable. In this case, it's impossible for us to do this because there are two y variables, and this guy has a cubed power to it. So the only way to undo the cube power would be cube rooting everything, which would mean cube rooting both sides of the equation. But this second term with a y in it would be trapped inside of there, and we can't get rid of them. So there are certain implicit form equations that we just can't rewrite in that explicit form. So when we come across that, it doesn't mean that we can't find the derivative. We just can't do it with our normal process. We have to do a little bit of extra work. So this new process for finding the derivative of an implicit form equation, we give it the not much of a surprise name of implicit differentiation. Okay. And before we get into this, it's not super complicated. It's just a little bit different. There's really one key change that we have to make. Okay. The algebra involved is actually far more complicated than the calculus that we do. So for implicit differentiation, when we take the derivative of a function in explicit form, everything works out nicely because we're taking the derivative with respect to our input variable, which means when I do the power rule to stuff with x, I want to know how does this pattern change as the x values change. So when those variables match up, it's not a complicated process because the variable that I'm concerned with is the variable that we're taking the derivative with respect to. So for example, when I take the derivative with respect to x of x cubed, that's just the power rule of 3x squared. However, if I tried to take the derivative of y cubed with respect to x, this is a pattern of the output values. Now it's a cubic pattern, so we know that the derivative of any pattern of x cubed, y cubed, whatever it is the old power brought down as the new coefficient, the old variable raised to one less than the old exponent. So that part is true no matter what I'm raising to the third power. We've seen this in the past with the chain rule when we used u's. It's still always going to be that way. The difference is the chain rule says that when our variable of differentiation does not match up with the variable that we're taking the derivative to, we have to apply the chain rule. Again, we've seen that when I've taken the derivative of u cubed in the past with respect to x, we always have to write that as 3u squared times du dx, or we traditionally use the u prime notation. Well, that's still true here. Instead of a u, it's a y variable. So I have to multiply this by the derivative of this variable with respect to x. Now, instead of using u prime notation, we know how another way to represent the derivative of the y variable with respect to x. And that notation is simply dy dx. So essentially what that means is that if I take any old rule problem that we've done in the past with x's, and I want to do that same derivative rule with a y, it's still the same math, it's still the same pattern, but because it's our output variable and these two variables don't match up, we will always be multiplying by a dy dx quantity at the end of that derivative rule. And that is, again, because we are accounting for the chain rule. The pattern structure overall is a cubic whose derivative is a quadratic, but the input for that expression is actually the output to some other function. So that's why we have to apply that chain rule. So if I had an expression that had x's and y's in it, it's just kind of a combination of these. When the variables match up and it's an x variable, then it's just a straightforward derivative. So d dx of x would just be 1. But when we take the derivative of non-x terms, so anything with y in it, then we have to apply the chain rule. So if this was the derivative of 3x, that's a linear pattern, so its derivative is a constant, and that's still true, but we have to account for how y changes as x changes, so we multiply by dy dx. Same thing if I had x times y squared. This is a product of two quantities, so we would use the product rule. But any of those factors of that product that match up with the variable of differentiation get taken the derivative of in a normal way. So derivative of x is just 1. But any of them that don't work out or don't match up, like y squared, we have to apply the chain rule. So y squared's derivative is 2y by the normal power rule, but the derivative of y is dy dx. So my insides plus my outsides would give me y squared plus, when we multiply all these variables together, keep them in alphabetical order. So we'll always put x's before y's just to stay consistent and help us not lose anything. So we get 2xy times dy dx. So once you guys pick up on that process of just training yourself, every time you come across a y variable, whether it's in the argument of a trig function or a natural log or an exponential, or if we just have polynomial power terms that use y as the base, anything with a y in it to start, its derivative has to include that dy dx. And again, that's just us doing the chain rule, but we're doing it for the y variable instead of a u or an x. And if you realistically think about this, technically, we could still do the chain rule every single time. But when we do it with variables that match up like this, the derivative of x as x changes If you really think about it, we could really express that as dx dx. So if you wanted to kind of follow the same structure with the x variables as we do with the y's, you would get the expression of dx dx as this extra factor. But this is saying a quantity of change is divided by itself. So it really just has a value of 1, which is why we don't really make you guys write that every single time. When Newton and Leibniz were going through this hundreds of years ago, they accounted for all of that, and they realized that when those variables match up, this quantity becomes irrelevant, and it's unnecessary for us to write that extra factor in there. So just know that when we take the derivative of x expressions, we really are doing the chain rule still. It's just not necessary to write it out because it's always going to be 1. So this is how we take the derivative of expressions with x's and y's mixed in there. But what we're going to be dealing with are actual equations. So we've got stuff on both sides. So general guidelines, the process for doing this. We're going to start with an implicit form equation. So that means x and y's are mixed together. Nothing is isolated. So we're going to take the derivative of both sides with respect to x. So you're going to see me put big brackets around the entire equation, and then we're going to ddx everything. So when we do that, we're going to go through just like we did here, take the derivative of every single term on both sides. But once all the calculus is done, these 3 steps are all about algebra. There's no calculus involved after we take the derivative. So the rest of this gets a little complicated. If our goal for this is to actually end up with a derivative equation, so dy dx, that has dy dx isolated. So that means the other side can be a mixture of x's and y's, but we actually do want dy dx by itself. So to do that, we have to collect all the terms in the equation that have a dy dx factor onto one side. We always choose the left because that's easiest to organize it. And then we move all the non-dy dx terms to the right side. And then we can factor out the dy dx factor from everything that we had on that common side, which leaves us with a group, or may just be one factor that we can divide out. And so we isolate our dy dx. So it might be hard to visualize exactly what all this is going to look like, but just know these steps are here. So when you're trying some problems on your own, you guys can always refer back to these to help you guys clear up any confusion that you have. So let's give this first example a try. So we're going to find dy dx given that this relation is true. So again, when it's not solved in explicit form, we tend to refer to them as relations because we don't know that this equation actually passes our function rule, which remember, some of these crazy relationships can actually end up having some really weird shaped graphs. In fact, why don't we go ahead and try to look at this guy real quick. So you can see there are, -4. There's some really weird graphs when we start to mix x's and y's. And you can see this guy actually is not a function and it fails that vertical line test. So that's why you just have to be careful about the wording of this. Our original equation is a relationship between x's and y's, but it's not a function. Again, a function has only one unique output for each input, and that's not the case here. So there are certain values of x, like this guy, that will produce a value down here and up here as well. So again, that's the difference. But that doesn't mean that we can't still come up with an equation that describes the rate of change for this graph. The only difference is you can see here that picking this point, actually, let's pick this one. So this point, if I wanted to know how the graph is changing at that point as I move left to right, reading it, it still has a slope because it's still a curve, but which x value I pick or which point that uses that x value really matters because when x is -2, there are actually 3 different points on this graph, and each one has a different rate of change. So what that means is the equations for dy dx, when we have an implicit relation like this, they actually depend on x and y values. So we actually have to know the whole coordinates of a point on these curves, and we're going to plug both the x and the y coordinates into the derivative whenever we want to know the slope of the tangent line. So there are some big differences between explicit form functions that we've worked with and these implicit relations. But if I just want to know the equation for dy dx, now I'm going to ddx the whole thing. So I want to know the change with respect to x of all of this. So again, each term one by one. Y cubed would turn into 3y squared, but I have to account for how y changes. So there's the dy dx plus 2y. This is the derivative of y squared, but again, it's a y term. So multiply by dy dx minus 5 is the derivative of y, but again, we have to account for the change in y. Then x matches up, so just a normal derivative. This would just be minus 2x. And then remember, any constants automatically turn into 0. So that's all of the calculus. You guys are going to do calculus one time for these problems, at most two if we want to look at a second derivative. But the calculus is not that difficult here. The hard part for all of these is going to be the algebra manipulation. So now our job is to make sure that all of the factors, or excuse me, terms with a factor of dy dx are on the same side of the equal sign. So right now, this one worked out nice. All of them are already on the left side. So we want the dy dx terms on one side. The non-dy dx terms actually need to go over to the other side. So to get rid of negative 2x, I'm just going to add it to both sides. So I'll have a 2x over here. So once this guy is gone and moved over, it leaves me with these three. And since all three of them have a dy dx factor in there, I'm actually going to pull that dy dx factor out from all of them. Doing so just leaves the other pieces behind. So what will end up happening is this little group that is being multiplied by the dy dx, it's always just going to have the x terms and the y terms that were a part of the previous step. So we're just removing the dy dx factor. By doing that, now I am free to get rid of this group that dy dx is being multiplied by doing the opposite. So we simply just have to divide both sides of the equation by whatever is inside of that group. In doing so, we cancel these two groups out. It leaves dy dx by itself. And so we are left with dy dx equals this fraction. We have lots of derivatives or dy dx equations that end up being fractions because of this process, because we end up moving some terms over and then dividing by a group of other terms. Most of these dy dx's actually end up being some kind of fraction. So this guy is the derivative of the original relation. So again, what this does, this guy will tell me the slope of the original equation's curve at any point. So with explicit form equations, we can tell you the slope at any x value. All I need to know is the x value because I'm guaranteed, because it's a function, that for each x value, there's only one point on the graph. But if I wanted to do that for this guy, I'd actually have to know both the x and the y coordinates. So I've got a couple points highlighted here, but that one's got some ugly decimals. Let's say I wanted to use this one. This one's a pretty simple one. So if I wanted to know the slope of the tangent line to that curve at that point, I would have to use negative 2, 0 in here. Now, there's a notation that is used often when I use dy dx. If I was working with function notation and I wanted to put something in, I remember I have these parentheses, I can just plug in the x coordinate, and that would tell you plug 2 into the derivative. But there is no like parentheses or input spot with this dy dx notation. So oftentimes what you guys will see being done is there's a notation where I can draw a really big vertical bar after a quantity like this. And down at the bottom, I can put whatever information I want to substitute into it. So for example, I'm going to put, oops, I already messed that up. I'm using the coordinates negative 2, 0. So I'm actually going to write the coordinates negative 2, 0 down there. And what that means is I'm substituting negative 2 in for x, 0 in for y. And now I'm going to do, whoops, not sure how that happened. I'm going to get rid of, okay, so it doesn't like that. Chasing commas. Just means I'm going to take those coordinates now and substitute them into this equation for x and y respectively. So that would give me 2, negative 2 over 3 times 0 squared plus 2 times 0 minus 5. Or we get negative 4 over 0, 0 minus 5, so negative 5. or 4/5. So again, what this tells us is that the slope of this curve at the point -2, 0 is 4/5, which if we go back and look at the graph, again, at that point, I know this is a little weird because it looks like this is kind of working backwards if you kind of read it left to right like we normally do. But for at any given point when we are determining increasing or decreasing, we have to start at that point and then look before and after, are we increasing or decreasing? So even though it kind of looks like this path is going right and then it comes back left and then it goes back right again, we can't read it that way. So at any given point, we have to start at points to the left and to the right. And locally, this guy is increasing at that point, and it's increasing at a rate of 4/5. So in fact, we could actually create the equation of the tangent line, y minus our y coordinate at the point of tangency equals our slope times the quantity x minus, oops, x plus in this case because of the -2. So you guys can see that is our tangent line at that point. So just like we just talked about, again, our dy dx equation, it still represents the slope of the tangent line to a curve. It's just not the slope of a function's curve now. It's just a relation. So we still interpret the results the same way as we did before. It's just now we go about finding it slightly different. So we're just going to take a look at a few more examples here with applications to this process. So for this one, I do want you to find the slope of the tangent line to this function's graph, excuse me, this relations graph at the point √2, -1 over √2. So one thing to keep in mind here, if I had given you a function and asked for the slope of the tangent line, then all I would have to give you is the x coordinate. But because this is a relation, we have to know specifically which coordinate, x and y coordinate, we're looking at. Because if we take a look at this graph, this function, or excuse me, this equation is again not a function because it fails a vertical line test. So for any particular value of x, like √2, which is like 1.41-ish, somewhere around in here, there are 2 points that use that x value. So we would actually need to know which one we're talking about, because if it's this top one, that curve is decreasing and dy dx would be negative. But if it's this bottom one, the curve is increasing at that point, so it would have positive slope. So we do need to know both coordinates when we are evaluating dy dx. So now that we have all that straight, now let's just jump in and do this math. So first we're going to ddx whole thing. Derivative of x squared is 2x. Derivative of 4y squared would be 8y, but we have dy dx. And then derivative of any constant is 0. So this one has less parts to it, so it's a little bit more straightforward. I can move the 2x over, so I'd end up with -2x over here. There's only one other term, so there's no factoring involved here. It's just I've got my dy dx multiplied by 8y. I don't have to change up the order. I just wanted to change it. I like having the dy dx out in front, so it makes it a little bit easier to see what it is I'm dividing away. That's just a personal preference. So I'm going to divide both sides by 8y. These cancel, and then we just need to reduce. So -2 over 8 reduces to -1x over 4y. So that is my reduced version of the derivative dy dx. Now I'm going to use these coordinates. So again, I'm going to use this vertical bar notation. I'm going to substitute, oops, not square root of x, square root of 2 in for x, and then -1 over √2 in for y. So that gives me negative square root of 2 for x over 4 times -1 over √2 on the bottom. So this is like a complex fraction. There's a few different ways that I can go about simplifying this. The most straightforward method is just get rid of this fraction by multiplying by its denominator, but I have to do that on top and bottom of the larger fraction so I don't unbalance things. So in the top, that just turns into -2. And then on bottom, I've got two things I need to multiply here. First off, the roots cancel each other out, but then I have the 4 and the -1, so we end up with -4 down there, and this reduces to 1/2. So again, that's all I wanted to know. I just wanted to know the slope of the tangent line. So if I were to go to this graph and take a look at the point square root of 2, negative 1 over square root of 2, you guys can see, oops, that is a period, not a comma. There is that point on the relations curve right here. And now we know the slope of that at that point is 1/2. So again, this problem doesn't ask us to do it, but if I needed to come up with the equation of the tangent line, I have everything that I need. I know my x and y coordinates, so this would be y minus negative 1 over root 2, or y plus 1 over root 2, equals the slope, which we just found using dy dx to be 1/2 times x minus the x coordinate, so square root of 2. So there is our tangent line. And again, the slope of the curve is the same as the slope of that tangent line. That's what we're using dy dx to find the value of. So pretty straightforward. Again, as far as the implicit differentiation process goes, it's going to vary from one problem to the next, how difficult the calculus part is. And the less parts means the calculus is pretty easy. That also is probably going to mean that the algebra side is going to be fairly easy as well. All right, so we did a pretty easy one. Now we're going to look at definitely a more complicated one. So we want to determine the slope of the graph of 3 times the quantity x squared plus y squared equals 100xy at the point 3, 1. So this is a mouthful. There is a lot going on in this problem. So first step, though, is I'm going to try to take the derivative. Now, the left side is actually just all one term. So the structure of that term, if you kind of read through it in a different way, it basically says 3 times something squared. Well, thinking of it in those terms means I can actually write this as a U problem or a chain rule problem. So 3u squared is the structure of that left side. So I'm actually going to use the chain rule. Yes, we will use the chain rule inside of this guy because of the y stuff, but we don't necessarily need to always redefine the y stuff in terms of u and u prime because it always is going to follow that same format where u prime is just dy dx. But in this case, my u is the inside of that group, so x squared plus y squared, and u prime would be 2x plus 2y, but then again, we do the chain rule with the y stuff, so we also have that dx. So we know the derivative of 3u squared would be 6u to the first times u prime. Now I'm going to get rid of that first now that I've said it, just because I don't want to mix it up with the prime symbol. So that is what we need to create for this left side. So 6 times my u is the x squared plus y squared group, but then u prime is also a group itself. And this is where this problem is really going to get tricky. Okay, we'll come back to this side here in 1 minute. But that is the derivative of the left side for now. We're going to manipulate it here in a minute. On the right side, I have one term as well, 100xy, which is a product. So I'm going to set up a product rule. 100x, its derivative is 100. Y, its derivative is dy dx. Insides plus outsides. Yuck, that looks really bad. And we'll leave it. Not the end of the world. We end up with 100y plus 100x dy dx. So calculus is done. We did all the calculus we need to. We found derivatives of everything. But now we need to try and manipulate this guy. And we've got a few issues. First off, there are dy dx's on both sides of the equation. So my first goal is to be able to get the dy dx terms on the left side. Everything else needs to be on the right side. But the issue with that is this guy is trapped inside of this big group. It's also attached to 2y in this term, but the larger issue is it's trapped inside of this group. And some people may be looking at it right now and thinking, well, just divide by this stuff, move this stuff away, and then we can lose the parentheses. The problem with that, though, is if we were to divide by these two factors on both sides, that would then trap this dy dx in the numerator of that fraction, and then we won't be able to get that one by itself. So you're going to be stuck one way or the other if we don't do something special here. So this may not be something that you guys have done a lot of in the past, but remember that if you multiply a group of terms by something out in front, then you are allowed to distribute that to all the terms of the inside. Well, we're going to use that distributive property here. We're just going to do it in kind of a weird way, because out in front of this group with the dy dx, we have another group and a constant multiple of 6. So what I'm actually going to do is I'm going to multiply both of these things into both of these terms. It's going to look a little weird, but for the first round, if I take 6 times this group and multiply it by 2x, I can actually take the loose parts, 6 and 2x, multiply them together, and my result is 12x times the binomial x squared plus y squared. So that was the first distributive property, or first step, that is. Now I'm going to do the same thing with to the second term. Again, the loose parts, I'm going to take 2y and 6, multiply those, and we get 12y, and then I still have this binomial, and then I still have my dy dx. By doing what we just did, taking all of this stuff out in front and distributing it inside to each of those terms, now this dy dx is actually free. Yes, it's still attached to these other factors in this term, but that's an easy thing to solve. Because as long as I have my dy dx's all on the same side, then we know we can factor it out. And that's the big deal. Before we did this step, I could not get this guy by itself. I couldn't move this term left or right if I wanted to, because it was trapped as part of this product. Now it's its own term, and that term is not a part of a product anymore. So now we can continue. Let's just rewrite the rest of this right side. And now we're able to move the individual terms where we want them. So I need to move our 100x dy dx over to the left side. And this first term I'm going to move, because it doesn't have a dy dx, I'm going to move it over to the right side. So we're basically just going to swap these two. So if I do that, I end up with, now I'm going to write this all out in long form. This one's more difficult, and I don't want to confuse anybody. So we have our first dy dx term, and now we're going to subtract, because we're moving this guy over, 100x dy dx. And then equals, we still had 100y on the right side, but I'm subtracting this first term that I moved over. So 12x x squared plus y squared. So everything is where it needs to be. Now we can factor out our common factor of dy dx. Okay, now when I do that, they're removed from these terms. So what is left behind is all of this stuff. So this stuff is just a product of this term. So what I'm going to do 2 steps at once. I'm going to distribute the 12y into both of these guys and then write the result of what's left over here. So this would give me 12x squared y plus 12y cubed. That's the result of the distributive property here. And then minus 100x. So that's everything that would be left behind after removing our dy dx factor and putting it out in front. On the other side, I'm going to go ahead and do this distributive property over here as well. So 100y minus 12x cubed minus 12xy squared. So I have my dy dx factor by itself. Now I got to get that term by itself by dividing this trinomial factor from both sides. So my end result is 100y minus 12x cubed minus 12xy squared all over this guy. So 12x squared y plus 12y cubed minus 100x. So that is our derivative. Now, it can be reduced. We've got all of these terms are divisible by 4. So I'm going to do that just kind of out in front. So I would have 25y negative 3x cubed minus 3xy squared, 3x squared y on bottom, 3y cubed next, and then minus 25x. So doing that, because we need to know the slope, our next step is we're going to plug in our x and y coordinates in here. Reducing that out first will make this multiplication a lot easier to handle. We're going to try and do it without a calculator. We'll see how that goes. So this would give me 25 times 1 minus 3 times 3 cubed minus 3 times 3 times 1 squared all over 3 times 3 squared times 1 plus 3 times 1 cubed minus 25 times 3. All right, so let's do a little bit of that math. 25 times 1 is 25. 3 cubed times 3 is 3 to the 4th, or minus 81. 3 times 3 times 1 is minus 9. So this is really 25 minus 90, or negative 65 up top. And then on bottom, we've got 3 times 3 squared times 1, or 27. 3 times 1 cubed is just 3, minus 75. So we have 30 minus 75, or negative 45, which reduces to positive 13 over 9 once I cancel out that common factor of 5. So that is the slope of this tangent line on this curve at that point. We get 13 ninths. So now, just to add a little bit of extension in here, without going to Desmos and graphing this guy, if I were to look at this graph, I know two things for sure. First, at that point, this function has a slope of 13 ninths. That is what the math tells me by taking this derivative and evaluating it at 3, 1. What it also tells me is that curve must be increasing at that particular point. Otherwise, we would not have a positive slope from the value of dy dx. So always keep that in mind, that whatever the sign of that derivative or the slope of the tangent line is, that directly correlates to whether our curve is increasing or decreasing. All right, our next example says, given x squared plus y squared equals 25, we want to find d2y over dx2. So that is remember the notation for our second derivative, which means I need to do this dy dx process twice. Okay, and remember, there's no shortcut to go from the original equation to the second derivative. So we're going to have to go through this process twice. And I'm going to point out a couple things as we go. But step one is find the derivative the first time around. So we need to find an equation for dy dx. So if I ddx the original equation, that gives me 2x plus 2y equals, not 25, because of the derivative of a constant is 0. And I forgot my chain rule. Let's try that again. 2x plus 2y times dy dx equals 0. There we go. So again, simple pieces. There's not a lot of pieces to the original, so we only end up with two terms here. I'm going to move the 2x over and then divide by the 2y to isolate dy dx. So when I do that, dy dx, the 2x coming over would become negative 2x. If I have this 2y factor and I divide by it, and this guy disappears, we have 2y underneath of here. Always, I mean, it's always important to do it on a normal basis. It makes the math easier, but especially when you are going to find the second derivative, make sure that you reduce this guy as much as possible, because it will make the next step of calculus that much easier. And a lot of times where mistakes are made with these is students don't reduce everything out when they find the first derivative. It leaves extra factors in the second derivative, and it makes things much more complicated, or could lead to actually doing something wrong. So in this case, these 2's reduce, and I'm left with negative x over y. That is the equation for dy dx. If I wanted to just simply know the slope of the original curve at a given point, that is the equation that I use. But if I wanted to know the second derivative, so if you think about it, first derivative tells me the slope of the original graph. This guy is the change of the first derivative. So d2y dx2 is telling me how dy dx is changing. So in other words, this equation's value would tell me how the slopes of the original graph are changing. So not just is the original graph increasing, but is it getting steeper or is it getting flatter? That's the kind of mindset we use when thinking about this second derivative. And we've got a lot more exploring to do with that second derivative in the sections and units to come, but just to give you a little bit of frame of reference for what this quantity is going to tell us. So to actually do it, though, instead of starting over from scratch, we're going to use this equation as our starting point. So we are going to take the derivative with respect to x of dy dx. So remember, notationally, if we kind of look at the top, there are two d's here, so that's where the d2y notation comes from. There are two dx's, that's why we write it as dx2. So that's what we create on the left side, d2y dx2. On the right side, though, it's just like a regular equation. I need to come up with the calculus for it. So this is a quotient, so I'm going to use the quotient rule. Negative x's derivative is -1, y's derivative is dy dx. So insides minus outsides for the quotient rule. So this will give me -y. Minus is the normal setup, but because this is a negative product, it will become plus x times dy dx. All over the original denominator squared. Okay? So if you notice, my d2y dx2 equation has a dy dx quantity in it. We don't want that. We don't want to have to, if I wanted to evaluate this equation, I would have to take the x and y coordinates that I'm plugging in for these three spots and then go back to dy dx, plug them in here, get a number, and then plug that in here. That's a lot of extra stuff to do, and it's not a good, clean, simplified way of expressing the quantity of d2y dx2. We want it just in terms of x and y. So anytime that your dy dx has a y variable in it still, your next derivative will have a dy dx, or the previous expression in there somewhere. That's just how the chain rule works. And that is true for every subsequent derivative on and on and on forever. So after we've done the calculus, again, now this is just algebra. Now I need to go and replace my dy dx expression with what it's equal to. So that's what we're going to do. So we get d2y dx2 equals -y plus x times what dy dx is equal to, -x over y. For some reason, that doesn't want to stop connecting. And now points are going to run away from me. So now what we need to do is simplify this. So remember that when I have a fraction as part of a term inside of a larger fraction, we refer to that as a complex fraction. The simplest way to get rid of a complex fraction is multiply the entire numerator and denominator of the outside fraction by this complex fraction's denominator, so the little guy inside. So basically, I'm going to multiply everything up top by y and the bottom. In doing so, everything that is not a part of that mini fraction is going to get a new factor. So -y times y turns into -y squared. But when I send it to this stuff, these guys are just going to cancel each other out. Again, that was kind of the point. Distribute here, here they cancel. So that just gives me x times x, or -x squared. And then on bottom, y squared times y gives me y cubed. So technically, that would be a perfectly fine place to stop. There's not really any simplifying with the terms that are in there right now. However, there are certain implicit form equations that you can start with where, because of the form I'm starting with, their derivatives have a particular form that there's a tiny little extra piece of simplification that we can do, and it's all tied between these two guys, the original and the second derivative. If you look carefully, the original equation says the quantity of x squared plus y squared equals 25. Well, this guy is very similar to what is left in this numerator. But what is different about them is both terms are now negative. Well, if positive x squared plus positive y squared equals positive 25, then -x squared plus -y squared, or I can rewrite this as -1 times x squared plus y squared. This is the same thing as 25, and that relationship was established by the original equation. So I can actually swap those two out from one another, which makes my second derivative much easier to work with. So this is actually equivalent to -25 over y cubed. So essentially what that is just kind of a heads up that when you're working with this implicit differentiation method, there are some times where you go to find that second derivative that there could be a substitution possible between the original function, or excuse me, the original equation and that second derivative. It's not a guarantee, doesn't happen all the time, but it is worth taking a look to see, can I factor something out of the top of this guy and swap it out with an equivalent form of the original equation. So in this case, this is the simplest version for d2y dx2. Our last example is, it's actually not strictly implicit differentiation, but this is a way that we can actually take the technique that we were just practicing and use it in an explicit form to help us. So there are some functions that start off in explicit form that, using explicit form rules alone, would actually be a really complicated derivative process. So the way around that is we actually use logarithms and some of their special properties to help break apart all the complicated stuff that's in there. But in doing so, it would require us to use implicit differentiation. So we use logarithms, break the equation apart, use implicit differentiation for the calculus side of things, and then we have to do some sophisticated algebraic manipulation to put all the pieces back together so that we can write our derivative in explicit form. So that's one really big important thing to remember. Because my original equation is y equals some function of x, I need to make sure that my dy dx is also some function of x, but the derivative of that function. So that's the really important part here. So we're not done after we just do the calculus. We can't just leave things. So to do this, what we're going to first do now, just to explore what would be necessary. If I did not use this logarithmic differentiation process, this is a quotient first and foremost. So my first piece would be a binomial squared. That would require the chain rule to find its derivative. The second piece would be a square root function. That would require the chain rule along with that complicated format of u to the 1/2. That fractional exponent produces a negative square root or a negative fractional exponent, which means we got to put that down to the bottom, and we have the chain rule involved in there as well. So then we have to do all the quotient rule process. It can be very, very time consuming to do all of that inside of one problem. So the structure of these kinds of problems where logarithmic differentiation is helpful is typically going to be a quotient, or you could see a really big product of multiple factors. Sometimes you'll see products in the top or bottom and it still be a fraction. So when they're a mixture of a whole bunch of complicated stuff, if you think about what the logarithmic properties say, remember we have three properties for logarithms. When we have an argument of a product, I can separate that into natural log of A plus natural log of B. If I have a quotient of factors, then I can separate that as natural log of A minus natural log of B. And then remember, if an argument is raised to a power, then that power can come down as a coefficient to that logarithm. So if the mixture of pieces in the original look like those properties hiding, then we can actually use this method to help us. So to get started with the process, we need to actually make both sides of an equation the argument of a logarithm. Technically, it doesn't matter which base you use, but the rule for natural log is definitely the easiest, so that's what we're going to use. So if we do that, then what we end up with is natural log of y equals natural log of all this stuff. So x minus 2 quantity squared over square root of x squared plus 1. So the left side, there's not really any properties that we can do. We're just going to leave that guy alone for right now. But the right side, that is where we can apply all of these properties. So when we first separate it, this would become natural log of the top, so x minus 2 quantity squared, minus natural log of the bottom, square root of x squared plus 1. So then there's not really a product in any of these, but we do have exponents on both of these arguments. So then we can take it one step further. The 2 comes down, so this is 2 natural log of x minus 2 minus this square root is the 1/2 power, so that comes down in front as well. So we get 1/2 natural log of x squared plus 1. Yikes, if my pen doesn't mess up, that would look fine. So now that everything is simplified, so we've done a lot of algebra up to that point. Now each one of those logarithms should be a very straightforward u prime over u format. So the only exception to that one, so again, normally we write natural log of u's derivative as u prime over u. The only exception to that is when we do the natural log of y, it's actually easier to write it in the 1 over u times u prime format because in this case, our u is really y, and so the derivative of that we write as dy dx. So it's kind of complicated or confusing to put that fraction up top. So that's why we're going to choose to write this derivative in the other format. So we are ready, though, to ddx this equation. So left side, we are going to get 1 over y. Not sure why it keeps doing that. Pain in the butt. We get 1 over y times u prime, or the derivative of y dy dx, and then equals. So each of these guys is then going to have that u prime over u format. So I still have the 2. Remember, these kinds of multiples stay there. But then x minus 2 is the first inside. Its derivative is just 1. And then minus 1/2 times the second guy. X squared plus 1 goes down in the bottom. Its derivative is 2x. All of the calculus is finished now. So now what we need to do, though, is simplify all of this. And there's a few stages to this process. The first of which is condensing all of these fractions on the right side down to one fraction. So in order to do that, I'm going to clean this up a little bit. So 2 times this fraction, I'm actually just going to rewrite this as 2 in the numerator. And then 1/2 times 2x, that actually is going to cancel these guys out. So what we really have is 2 over x minus 2 minus x over x squared plus 1. So remember that when we go to combine fractions, they need to have the common denominator. X minus 2 and x squared plus 1 don't share any common factors. So in this case, our least common denominator is just simply their product. So this whole time, nothing's going to change on the left side. But on the right side, I'm essentially multiplying each of these fractions by the other's denominator, but in top and bottom. So that's how I will achieve that common denominator. So for the first one, I get 2 distributed into there. So I get 2x squared plus 2. And then remember, this is a minus. So I'm going to be really distributing negative x inside of here. So this would be minus x squared plus 2x. All over that common denominator now of x squared plus 1 and x minus 2. Now, I personally choose to leave the denominator in factored form because of something that's going to happen here in a minute. You're going to see there is some more simplifications that occur with those guys on bottom, so it's best just to leave it alone and not try to multiply it the whole way out in the denominator. The top always multiply out because now we can simplify this by combining like terms. So 2x squared minus x squared gives me 1x squared plus 2x plus 2. You can check to see if that factors. It would be very rare for this to actually factor or factor and lead to anything meaningful and cancel out with the bottom stuff. Because of how these guys are created, it's very unlikely that it's actually factorable. And in this case, it is not. So we simplified all of the stuff on the right side. So that algebra part is done for right now. But now our issue is we need this in explicit form. So there are 2 issues with that right now. First off, dy dx is not by itself. So first, we need to fix that by getting rid of the stuff over here. So it's being multiplied by 1 over y. So to fix that, we just multiply both sides by y. So that's a pretty simple fix. But the second issue that is a result of that is we started with an equation that was in explicit form, where y was strictly a function of x. And because it's a function of x, if I had chosen to, I could have used function notation, f of x equals all this stuff, which means I need to be able to write my derivative as f prime of x is equal to all this stuff. You can't do that if you still have y variables in the expression for the derivative. So we need to make sure that we are getting rid of any of those y variables. And how do we do that? Well, we know something that y is equivalent to because of the explicit form equation that we started with at the beginning. So that is always going to be your last step here. We're going to swap out y with what it's equal to and then use that new stuff to do any last minute simplifications. So we still have this big fraction here, but then instead of multiplying that by y, we will be multiplying that by x minus 2 squared over square root of x squared plus 1. And now this is where we need to go through and do some simplifications. And this is the reason why it's best to not multiply out your bottom, because this denominator is always made up of the original pieces from the explicit form of the equation. So whether it was something in the top or the bottom, there's some way to cancel out or rewrite the product and quotient of these mixed factors. So for example, there is an x minus 2 factor on top and bottom, which means that guy cancels out with one of those. Then there's an x squared plus 1 to the first power times an x squared plus 1 to the 1/2 power. Because they're being multiplied, we can actually group those together and combine their exponents. So what my end result is, now in the numerator, some people may choose to multiply this out. Others may leave it as the trinomial times the binomial. I'm just going to go ahead and multiply it out. That would give me x cubed minus 2x squared plus 2x squared, so they actually cancel. Minus 4x plus 2x, so minus 2x. And then 2 times negative 2 is negative 4. So I didn't need quite that big of a line. And then on bottom, we would have, again, x squared plus 1 to the first times x squared plus 1 to the 1/2 would give me x squared plus 1 to the 3/2 power. That is our final form of the derivative of y in explicit form. Everything's in terms of x. There are no y's left over, and there's really no more simplifications that I can do to this guy. This is the final form of the derivative.